This is section 2.6, algebra functions and composite functions. This first slide right here shows a graph on fixed and variable costs. We see that the green line represents the total fixed cost, the blue line represents the total variable costs, and then this black dashed line represents the total costs, essentially adding together the function for varying cost and fixed cost. And so that's something we'll be talking about in algebra functions, where we're adding, subtracting, multiplying, and dividing functions. This next slide is asking us to find the domain of the function. So just revisiting what we mean by domain, we're saying, okay, what are all the possible x's in this function? It is already graphed, but just to revisit the graphing portion of this, we'd press 5 to get into that graph. Oh, let me delete this out. Okay, so it's negative absolute value. So I'd press Shift 4 to get to my catalog, and then I'm just going to scroll down to ABS, which stands for absolute value. And then we have X minus 4. Notice that I use negative in front of the absolute value and then this subtract symbol for, oh, and it's not subtract, so I'm glad I caught that. But if it was subtract, I would put use this button instead. That will sometimes give you an error if you use the wrong button. And then plus 2 outside of, so arrow out, plus 2, F6 to draw, and yes, I see that same graph that we see pictured down below. And so when we're talking about domain, all of the x's, right, what is the farthest left my graph will go in x values, and then what is the farthest right? Well, it's coming from negative infinity and going to positive infinity, so this would be my answer right here. Again, on this slide, they're asking for the domain of the function. So we would go ahead and enter that into our calculator. I'm going to exit back out to this screen where I can enter in the function I want to be graphed. I have x squared minus 2x minus 5. Execute to go to the next line, and then F6 to draw it out. Remember, in regards to my domain, I'm just essentially asking how far left and how far right will my graph go. Well, you see that this is coming out from the left, so there's no end to how far left this will go, so it'll be coming from negative infinity. And then as this travels upward on the right side of the graph, it goes out further and further to the right. So D would be my answer. And notice that they give you some funky answers here, right? So be careful of that. Don't be like, oh, that's too simple. It can't be just negative infinity to positive infinity. If that's where all your x's, can go, then that's the answer. Quick lesson on 0 in the denominator. Little math humor here. It says, oh crap, who divided by 0? So if you understand that dividing by 0 is undefined, then that might have given you a little bit of a giggle. So 0 in the denominator, just to try to understand this a little bit, because a lot of people get confused on, oh, well, is it that I can't divide by 0 or 0 cannot be divided by something? So it's okay if we have 0 divided by a value. No matter what, that's going to be 0. But if we have any value, I'm just using 2 as my any value, divided by 0, then that's when it's undefined. I'm just going to put UND, since I can't fit undefined on there. So let's talk about this a little bit. If you can distribute, or it says you can distribute 10 cookies evenly to 5 different people. If I have a batch of 10 cookies, 5 people show up to my get together and I say, okay, each of you get an equal amount of cookies, I would hand them out and I'd say one for you, one for you, one for you, eventually distributing all 10 where each of the 5 people got 2 cookies each. If I had 10 cookies, but only one person showed up and I said, okay, I'm going to evenly distribute these out, I'd say one for you again, one for you again, all the way up until that one person got 10 cookies, right? So dividing. And then technically, if somebody showed up and let's say I burnt all my cookies, so I have 0 cookies and I distribute them to the 5 people that showed up, technically I can still evenly distribute that. I'd say, okay, no cookie for you, no cookie for you, no cookie for you, right? And all 5 people would get 0 cookies. But in that last example, it says you cannot distribute 10 cookies to 0 people. So I have these 10 cookies. Nobody shows up. I can't distribute those and almost like finish the process of saying, yes, all these cookies were distributed evenly. And that's why that's undefined. A corny way to remember it, but as I've seen with my students, a memorable way to remember it is if the 0 is under the line, it's undefined. I'm going to finish writing it. If the 0 is under the line, it's undefined. So if you see this, that might confuse you. You might want to write it out in fraction notation. But if the 0 is under the line, it's undefined. Okay, this slide pretty much says the same thing. 12 divided by 4 equals 3, because if I add 4 together 3 times, I can get back to 12. 12 divided by 2 is 6, because if I add 2 6 times, I can get back to 12. But 12 divided by 0 would be undefined because I can never add enough zeros together to get back to 12. Okay, so taking that into consideration, we have to look at the denominators here and say, okay, well, what is going to cause a denominator to be a 0? Because if we have a 0 in the denominator, it's undefined, right? We can't have that. It tells us to find the domain of this function. The function is f of x equals 3 over x minus 5. If we were to graph that, we would see this graph. Notice that there seems to be an imaginary line that runs here. And it's called a vertical asymptote. And this is where x cannot be, right? And if we look at it, we're approximately at 1, 2, 3, 4, 5. But I always say never just trust your eyes when you're looking at a graph, because something could be 4.75 and it could look like it's at 5, right? So I can then let me go ahead and graph this. Okay, so we'll do fraction, 3 up top, x minus 5 in my denominator. Draw it out. Okay, we get that same picture, right? This is in my graph, but if I go back out to my menu, so press menu, and I press 7 for table, and then F6 to actually see the table, it starts me at negative 12. I don't need all of that. And I can actually exit out of here and choose F5 for set and see it's telling me where my table starts and ends. So let's just start it at 0. And then we can end it at 5 because 5 is what I want to see, right? And then step is what unit it travels by. So I said by ones. Okay, I go back to my table. I go to 5 and boom, there's an error. Okay, so that's what you're looking for in your table. You're saying, okay, if there's an error there and it matches up with my graph here, then yes, 5 is accurate, that is what it cannot be. Okay, another way to do this is I can set the denominator equal to 0. So x minus 5 equals 0. Essentially trying to solve what would make it equal to 0. Add 5 to both sides, and I get x equals 5. Okay, don't let that confuse you. I just solved for what x cannot be, right? Because if x was 5, 5 minus 5 would give me 0 in the denominator, and as we can see from our graph and from our table output, it cannot be that. So when I go to answer in interval notation what my domain is, it can be any number under the sun, all the way from negative infinity up until we reach 5. But then after 5, it can pick back up and go all the way into infinity. So our domain will be negative infinity to 5, not including it, so I'm going to use parentheses, union, pick back up at 5, not including it, all the way to infinity. Now, for your union button, be careful because it just looks like a capital U, right? In MyMathLab, there is a specific button that is for union, and it sort of looks like just a wider capital U. But if you use just a capital U off your keyboard, it'll count it wrong, and you'll be completely confused why you got it wrong if, your answer looks exactly the same besides that union. So be careful of that. Okay? So again, we would graph this. For time's sake, I'm not going to graph it again since we have the picture here and the table. If you're like, hold on, how did we do that again? Please just go back to that last slide where I actually went in and showed you. So we get this. Looking at my graph, it looks, just from the naked eye, it looks like I'm at negative 3, x equals negative 3, and x equals negative 5. That's just my eyes, right? I'm not going to trust it from the graph. What I can do, though, is go to my table and see, okay, for my outputs there, do I get error? And the reason it gives me an error is because, remember, we cannot have 0 in the denominator. And so what it's saying is, if I put negative 5 in for my x, or negative 3, in this case we have 2 of them, then I cannot have an output because it would be undefined. Okay, and let's check it. Let's just see. So if I did negative 5, I'm just plugging in negative 5 into x here. I'd have 25 minus 40 plus 15. 25 minus 40 is negative 15. Negative 15 plus 15, guess what? Equals 0. And my denominator cannot be equal to 0. Same thing would happen if I plugged in negative 3 for that x. I would get a denominator of 0. So let's go ahead and write our domain in interval notation. So remember, it could be anything from negative infinity up until we reach 5, right? And then it picks back up, negative 5. It picks back up at negative 5, not including it, and goes all the way to negative 3. And then it picks back up right after negative 3 and goes all the way into infinity. So try to train your eyes by looking at that from left to right. What are all the places I could have an x value? Well, we said negative infinity to negative 5, union, negative 5 to negative 3, so that's this middle portion right here, union, negative 3 to infinity. If you see 3 parts of the graph, then you know that there'll be 3 intervals, right? But be careful, because if your window is not showing all 3 parts, then you might be like, oh, well, there's 2 parts, so there should only be 2 intervals. No, there's 3 parts here, so there's 3 intervals. So that's when we have x in the denominator. If I didn't have x in the denominator and I just had a plain old 5 in the denominator, well then there's not going to be a restriction on what my x can't be, right? Because it won't affect the denominator. But when I have that variable in the denominator, then yes, I have to determine what that variable cannot be in order to keep that denominator from being 0, which would make it undefined. Okay, the other scenario we have to look at is when we have x underneath the radical, right? So when we have x underneath the radical, we need to take this into account because you cannot have a negative value underneath the radical. It's not that you can't have a negative x, just this entire value right here cannot be underneath the radical. Because remember that when we find the square root, let me specify if we're finding the square root of something. So when I'm finding the square root of a value, I'm asking what value times itself will give me whatever the value is underneath the radical. So if I say, what is the square root of 9? You would tell me, well, positive 3 times 3 is 9, and so is negative 3, so plus or minus 3. But if I said, well, what is the square root of negative 9? Then you would tell me, oh, there's no answer to that because there's no value. Well, let me rephrase that. No real value, because we're going to talk about imaginary numbers. And so that's going to be another lesson. But there's no real number that can meet this because what number can I multiply by itself and get to negative 9? Well, negative 3 times negative 3 is positive 9. So that couldn't work. So that's why we have to keep the value, the entire expression, underneath the square root radical positive. Okay, it can be 0 because 0 times 0 is 0, but it cannot be negative. So we can graph this, okay, and they've already graphed it here. Okay, so shift to get access to that square root. I have 10 minus 2x. Execute it. Oh, I'm in a table. Let me go back out to menu, get in the graph. The good thing is when you enter it into the table, then it's in the graph, or vice versa. If you enter it into the graph, then it's already over into the table. Okay, so we get the same picture, right? Now, I want us to look at this. It seems to stop right there. So it looks like 1, 2, 3, 4, 5. Let's look how that affects the table. So let's go back over to our table. I want to change up our set a little bit because it looks as though I can't go past 5. Like x can't be greater than 5. So I'm actually going to end it at 10. We'll still have a step of 1. Okay, so as we can see, I can have an x of 0, 1, 2, 3, 4, 5, but watch, 6, 7, 8, 9, 10. Sure enough, after I pass 5, so 5 is okay, but after I pass 5, I start getting errors. Why? Well, look at that. If I put 6 underneath here, 10 minus 2 times 6, which is 12, 10 minus 12 would get me a negative value, right? But if I have a 5 there, 10 minus 2 times 5, which is 10, then I would get a 0 underneath the radical. And notice that my output, when I had 5 as my x, was 0. So that works, okay? So that means that for our domain, I can have any value coming from negative infinity up until 5, but including 5 now. So domain would be negative infinity to 5. And what are we going to use? Brackets, because we're including 5. Be careful here because many students get used to using the parentheses for the vertical asymptotes like we saw when there's an x in the denominator, and then they want to continue that here. So for this section, the domain will always be negative infinity to positive infinity, unless there's an x in the denominator, which then we have to decide, okay, what can x not be to keep from this denominator from being 0, right? Because we can't have a 0 in the denominator. Or if there's an x underneath the radical, because we cannot have a negative expression underneath the radical.